Swayam Prabha. Digital India. Educated India.
Now, we are going to discuss projection. So, already we come across the Gram-Smith orthogonalization process with how they are ortho-normalized and orthogonal of one vector to the another, and further we have to understand what is the meaning of projection. Let us start with components and projection. Suppose you take a vector v and u like that, and one is project on the other. So, this is called it as projection of u over v. So, given two vectors u and v, we can ask how far we will go to the direction of v when we travel along u. So, the distance travel in the direction of v while transversing u is called a component of u with respect to v and is denoted by component of u over v. So, the vector parallel to v with the magnitude, the component of u over v in the direction of v is called as projection of u into v and is denoted by projection u over v. So, rather we can denote this as a component of u over v equal to norm of projection of u over v. So, this is the definition of component of u over v equal to norm of projection of u over v. Note that the projection u over v is a vector and a component of u is a scalar. Then from the picture we have a component of u over v equal to norm of u and to cos theta. So, we wish to find the formula for the projection of u into onto v, that is dot product of two vector u dot v equal to norm u norm v cos theta. Thus, norm u equal to cos theta equal to u dot v by norm v. Therefore, component of u over v equal to u dot v by norm v. So, the unit vector in the same direction v is given by v by norm v. So, the projection of u over v is equal to what? The inner product u dot v by norm v square into v. So, this is the definition of component of u and a projection of u. Component of u is simply u dot v by norm v, whereas projection of u over v is nothing but inner product u dot v by norm v square into v. So, let us go to discuss one example. Find the projection of u equal to I plus 2j onto v equal to I plus j. Now, you take a u vector and a v vector, dot product them u dot v equal to 1 I into I, that is 1, 2 into 2j into dot j is 2, therefore 1 plus 2 equal to 3, therefore norm v square is equal to root of 1 plus 1 square plus 1 square equal to 1 plus 1 equal to 2, therefore norm v square equal to root 2 the whole square equal to 2. Therefore, projection of u over v equal to inner product u dot v by norm v square into v, which is equal to 3 by 2 of 1 I plus j, which is equal to 3 by 2 I plus 3 by 2 j. So, let us go with some more example. Projection of u I plus 2j onto v equal to I plus j and find the projection. Now, you take a two vector u dot v equal to 1 plus 2j dot 1 plus j, which is equal to 1 plus 2 equal to 3, norm v square equal to root 2 the whole square equal to 2. So, projection of u dot v by norm v square into v equal to what? That is u dot v equal to what? 2, and then into v vector is I plus j. Therefore, norm v square is equal to 2, therefore 3 by 2 into I plus j, therefore 3 by 2 I plus 3 by 2 j. Next, find a projection of u over v where u equal to 1 to 1 and v equal to 1 1 2. Now, u dot v equal to 1 plus 2 equal to 5 and norm v square equal to root of 1 square plus 1 square plus 1 square the whole square, which is equal to root of 1 plus 1 plus 4 is equal to 6, root 6 the whole square is 6. Therefore, projection of u over v equal to 5 by 6 into 1 by 1 comma 1 comma 2. Next, find the component of u equal to I plus j in the direction of v equal to 3i plus 4j. Now, u you know, v you know, then dot product u dot v equal to 3 plus 4 equal to 7. Therefore, norm v equal to root of 3 square plus 4 square equal to root of 25 equal to 5. Therefore, component of u over v equal to u dot v by norm v, which is equal to 7 by 5. Now, next find the component of u equal to I plus 3j minus 2k in the direction of I j k. Now, u dot I equal to I plus 3j minus 2k dot product of I equal to 1, and u you know, right, u you know, and then j vector dot product them we have a 3, and then u you know and k dot product them we have a minus 2. Now, norm of I is equal to root 1 square 1, norm j, norm k is 1. Therefore, component of u over I equal to 1, component of u over j equal to 3, component of u over k equal to minus 2. So, that the use of the term component is justified in this context. Now, let us go to the example 2. If coordinates in the plane are rotated by 45 degree, the vector I is mapped to u equal to 1 by root 2 I plus 1 by root 2 j, and the vector j is mapped to v equal to 1 by minus 1 by root 2 I plus 1 by root 2 j. Find the component of w equal to 2 I minus 5 j with respect to the new coordinate vectors u and v expressed w in terms of u and v. Now, so this is the meaning of 45 degree, that is 90 degree, and convert to 45 degrees, so this is a 45 degree. Then we have a what, the vector w equal to 2i plus j. So, 2i minus 5j, and then v equal to minus root 1 by root 2 I plus 1 by root 2 j, and u equal to 1 by root 2 I plus 1 by root 2 j, and then the component of the vector can be expressed w in terms of u and v is this. So, this is the meaning of what, rotated by 45 degree, the mapping is like this. Now, you have to work with w dot u, which is equal to minus 3 by root 2, and w dot v equal to minus 7 by root 2, and norm u and norm v are equal to 1. Therefore, component of w over u equal to minus 3 by root 2, component of w over v equal to minus 7 by root 2. Therefore, w equal to minus 3 by root 2 into u plus minus 7 by root 2 into v. Now, we are going to discuss the rotation, projection and reflection. So, what you would expect, a rotation through an angle theta views that the point as being on a circle center at the origin and moves it along with the circle at angle theta. So, this is the meaning of what, the rotation. So, rotation is through an angle theta about the origin, and views that the point as being on a circle, right, arc center at the origin and moves it along the circle at an angle theta. So, how do we get the transformation that does this? So, in class I said the following: given a point x comma y, put it into polar form r comma theta, where x equal to r cos alpha and y equal to r sin alpha. Then the rotated from the new x coordinate is x, that is r into cos of alpha plus theta, and new y coordinate r into sin of alpha plus theta. So, the addition formulas for sin and cosine gives r theta of x comma y equal to r cos alpha cos theta minus r sin alpha sin theta for the x axis, and y axis r sin alpha cos theta minus r cos alpha sin theta. Simply expand cos of alpha plus beta equal to cos alpha cos beta minus sin alpha sin beta, like that. You have to do, corresponding value can be generated, and then we simplify x cos theta and y minus y sin theta will come for the x coordinate, and y coordinate minus x sin theta plus y cos theta will come for the y coordinate. Now, in vertical format, we can write this form as r theta of x comma y equal to x cos theta minus y sin theta and x minus x sin theta y cos theta, and then we can write into matrix form. So, cos theta minus sin theta and sin theta cos theta of x comma. So this represents the rotation of theta with respect to the x axis and y axis, and then corresponding we can write the rotation format in the matrix form. So, it is easier to check what the rotation does the two basis vector 1 comma 0, 0 comma 1. So, this is the way we can map from domain to codomain in the organ plane or Cartesian plane. So, fix that we have to fix rotation of 1 to x like that, and start from y 1 to 0 will go like this. So, this is the way we can start from what the rotation does the basis vector of 1 comma 0 and 0 comma 1. So, the point 1 comma 0 rotates to cos theta comma sin theta, so that the first column of the matrix of the transformation. On the other hand, 0 comma 1 rotates to minus sin theta and cos theta by some simple trigonometry. So, this is the second column of our matrix, giving the same answer as before. For example, if you want to rotate through 150 degree, so the transformation that does it is t of x comma y equal to minus root 3 by 2 minus 1 by 2 and minus root 3 by 2 of x comma y. So, the rotation matrix formula should be normalized or memorized. Now, the projection and the reflection are similar. For the projection onto a line, given a line L through the origin, we want a mapping that takes a point as an input and moving perpendicular to L gives the resulting point on that line. That is, for a point not on a line, we want the point on the line closest to the given point. For the reflection, we move through the line to get the point and equal distance on the opposite side. So, as mentioned in the class, one way to find a formula for reflection is as follows: given a line L and a fixed point P. So, this is the corresponding picturization of the given projection and the reflection, which is similar to one another. So, we construct the line through P perpendicular to the line, where this new line intersect L is the projection, the point Q. If we keep moving the same distance through L, we get the reflected point R. So, that the points can be explained here, that how the line y equal to phi x, right. So, y equal to phi x, this is a representation of y equal to phi x, then the point a comma b, and then the perpendicular L through the point a comma b, where y minus y1 equal to m into x minus 1 technique you have to apply, and then y minus b equal to 1 minus 1 by 5 into x minus a will generated, and we have a straight line. So, this intersect L with phi x minus b equal to minus 1 by 5 of x minus a, and then simplify minus 1 by 5 x plus 1 by 5 a. Further simplify, take LCM, and then you can get what 26 by 5 x equal to 1 by 5 a plus b. So, that is x equal to 1 by 26 a plus 5 by 26 b, and then y is a 5 times this, or y equal to 5 by 26 a plus 25 by 26 b. So, if we are projecting the point x comma y instead of a comma b, then we have p of x comma y equal to 1 by 26 x plus 5 by 26 y, 5 by 26 x plus 25 by 26 y. So, we have a what matrices 1 by 26, 5 by 26, 5 by 26, 25 by 26 into x comma y. So, this way we can having the projection of one point to the another. So, what about reflection? I think of things this way: we move from P to Q, we move P to Q, and then move the same distance along the line from Q to R, okay, the given below. So, how do we do this. So, you add Q minus P to P. So, to get P to Q. So, to get from Q to R, we add same quantity Q minus P, that is given P and Q. So, R equal to 2Q minus P will come. So, if P having the coordinate A comma B and Q already we deducted that the matrices like 1 by 26A plus 5 by 26B and 5 by 26A plus 25 by 26B, then 2Q minus P we can be generated. Therefore, 2Q equal to 1 by 13A plus 5 by 13B and 5 by 13A plus 25 by 13B minus of AB. So, that simplify, subtract it, so that 2 cross 2 matrix, that is 2 rows and 1 column will come. So, this matrix is the transformation is minus 12 by 13, 5 by 13, 5 by 13 and 12 by 13. So, this is the matrix, call it as a reflection matrix, and we have the property of A square equal to I, that is A is its own inverse. The reason for this is that if you do not do a reflection twice, you hope to other side of the line and then back to where you started from. So, that is doing a reflection twice leaves you unchanged, like flipping a light switch twice. So, there are other kinds of projection and reflection. One above are called orthogonal, a fancy word for perpendicular because you move perpendicular to the line. We would move in some other direction. However, for example, we could move parallel to the line y equal to minus x rather than the line perpendicular to L. So, this might be the new diagram like this. So, the calculation would be very similar. In this case, moving A comma B parallel to the line y equal to minus x means that we want to know where y minus b equal to minus of x minus a intersect y equal to phi x. So, this will happen when phi x equal to minus x plus a plus b, or x can be expressed as 1 by 6 into a plus b and y equal to 5 by 6 into a plus b, 5 by 6 into a plus b, y equal to 5 by 6 into a plus b. This new projection transformation would be t of x comma y equal to what? 1 by 6 into x plus y, 5 by 6 into x plus y. We have the matrix 1 by 6, 1 by 6, 5 by 6, 5 by 6. So, the reflection 2q minus p equal to 2 times of 1 by 6 into x plus y and 5 by 6 into x plus y minus x comma y. So, we have minus 2 by 3x plus 1 by 3y and 5 by 3x plus 2 by 3y, and the transformation is t of x comma y equal to minus 2 by 3x plus 1 by 3y and 5 by 3x plus 2 by 3y with matrix minus 2 by 3, 1 by 3, 5 by 3 and 2 by 3. So, again a square equal to a for the projection and a square equal to I for the reflection. So, this is the meaning of where the projection occurred and where the reflection occurred can understand. So, for the rotation matrix we can easily do that. So, rotating by theta counterclockwise is done using the rotation matrix, and r theta equal to cos theta minus sin theta and sin theta cos theta. If you want to go clockwise, then r of suffix minus theta equal to cos theta sin theta minus sin theta cos theta. So, now there is one very easy case for projection and reflection. The project onto the x axis or through the x axis, the formulas are x comma y maps to x comma 0 for the projection, x comma y to x comma minus y for the reflection. So, these transformations have a matrices as well. If we let P of V represent a projection and T of V a reflection, we could write these simple transformation in the matrix form P naught of x comma y equal to 1 0 0 0 of x comma y and T naught of x comma y equal to 1 0 0 minus 1 of x comma y. So, this is the meaning of what? Transformation from one point to the another. So, P represent projection and T represent reflection. Now, let us work out an example this way. We want orthogonal projection and a reflection through the line y equal to 2 by 3x. So, we have theta equal to tan inverse of 2 by 3. Of course, this is not a nice number, still we do not need theta, we only need sin theta and cos theta. By drawing the appropriate right triangle, I should have another figure. Here the side opposite theta should be 2, the side adjacent should be 3, the hypotenuse will be root 13, right. So, 4 square plus 3 square, 4 is 4 plus 9 is root 13, therefore, hypotenuse equal to root 13. Therefore, sin theta equal to 2 by root 13 and cos theta equal to 3 by root 13. Therefore, our matrices are what? R theta equal to 3 by 13 minus 2 by root 13 and 2 by root 13 and 3 by root 13. Therefore, P suffix theta equal to 1 0 0 1 0, R of minus 0 equal minus theta equal to 3 by root 13, 2 by root 13 minus 2 by root 13, 3 by root 13. So, the resulting projection matrix is simply multiply them for this, this and this. So, we have what? For first these two multiply, you have what? 3 by root 13, 3 by root 13, 2 by root 13, 0 0, and these two multiply of the matrix multiplication, then we have 9 by 13, 6 by 13, 6 by 13, 4 by 13. So, this is symmetry, you know that. Similarly, the reflection matrix is, you take this part is minus 1 and then do the process of same r theta and p of reflection, and then r of minus theta keep as it is, and then multiply them, we have what? The reflection matrix will come. So, we derived what is the meaning of projection matrix, and also we derived what is the meaning of reflection matrix. So, this is a technique we have to adopt. So, I almost never calculate projection and reflection matrix this way. I use the approach I outlined in the class of finding the line through a point a comma b orthogonal to y equal to mx, where the two lines intersect is p of a comma b. To get the reflection t of a comma b, I first figure out how far a comma b moved to get the projection. Find v so that a comma b matrix plus b equal to p of a comma b, which has solution v equal to p of a comma b minus a comma b. Then use the formula t of a comma b equal to p of a comma b plus v equal to 2p of a comma b minus a comma b. So, in the end I change a to x and b to y. This method avoids the radicals of the other approach. So, you should feel free to use whichever method you find easier. So, this is the meaning of the rotation based on the object in the plane about the origin, and if the rotation angle is positive, we rotate counterclockwise direction. So, this is a way of rotated 110.5 degree, and this first quadrant we have a original figure and rotate it in the second and third quadrant, it reflected like that. So, this is the corresponding robotic arm needs to rotate its joint in order to pick up the objects or to place them correctly. So, this we have taken the book Dyson-Roth, and then the rotation is a linear mapping, more specifically an automorphism of the Euclidean vector space that rotates a plane by an angle theta about the origin, that is, the origin is fixed point for a positive angle theta greater than 0 by common convention. So, we rotate in a counterclockwise direction, an example shown in the figure where the transformation matrix is what? Minus 0.38 minus 0.92, 0.92 minus 0.38. So, the important application areas of rotation include computer graphics and robotics. For example, in robotics, it is often important to know how to rotate the joints of the robotic arm in order to pick up or place an object, see the figure 3.15. real time application of how the rotation and reflection and transformation can get it using the linear mapping. So, in the figure 3.16 rotation of the standard basis in r square by angle theta. So, this is the what E1 vector you take it, E2 vector you take it, and then if you rotate it and it project with the help of the what phi of E1, we have a cos theta comma sin theta, and then further it reflect it. So, phi of V2 equal to minus sin theta comma cos theta. So, the rotation in r square we can generate it. So, further we have to deduct rotation r square. We have a what basis vector E1 equal to 1 comma 0, E2 equal to 0 comma 1 in r square, which defines the standard coordinate system in r square. We aim to rotate this coordinate system by an angle theta as illustrated in the figure. Note that the rotated vectors are still linearly independent, and therefore, there are a basis of r square. This means the rotation performs a basis change. So, rotation phi are a linear mapping, so that we can express them by a rotation matrix, and see the figure, and the trigonometry allows us to determine the coordinates of the rotated axis with respect to the standard basis in r square. So, we obtain phi of E1 equal to cos theta sin theta, and phi of E2 is minus sin theta cos theta. Therefore, the rotation matrix that performs the basis change into the rotated coordinate r of theta is given by r of theta equal to phi of E1 comma phi of E2, and this can be represented in matrix form cos theta minus sin theta and sin theta cos theta. So, this is a standard way of two dimensional in rotation corresponding the rotation matrix. Next, rotation in r cube. In contrast to the r square case, in r cube we can rotate any two dimensional plane about one dimensional axis. The easiest way to specify the general rotation matrix is to specify how the images of the standard basis E1, E2, E3 are supposed to be rotated, and making sure these images RE1, RE2, RE3 are orthogonal to each other. So, we can then obtain a general rotation matrix R by combining the images of the standard basis. So, in the figure 3.17 denote that rotation of the vector in R cube by an angle theta and about the axis. Therefore, you consider E1 and E2, E3. So, we rotate with the E3 axis, and the blue color shows that the rotated to the vector from E1 to E3 and E2 corresponding to this one we can rotate, right. So, this means this is the meaning of a rotation, how it occurs in the Cartesian plane. So, rotation about the E1 axis. So, R1 of theta equal to phi of E1, phi of E2, phi of E3, which can be expressed as 1 0 0 0 0 cos theta minus sin theta cos theta. So, this is the third one, that is a three dimensional effect of rotation about the the axis. Here E1 coordinate is fixed, the counterclockwise rotation is performed in E2 E3 plane. So, that is the meaning of 3.77. In 3.78 the rotation about the E2 axis, the corresponding matrix is cos theta 0 sin theta 0 1 0 minus sin theta 0 cos theta. So, if you rotate the E1 E3 plane about the E2 axis, we need to look at the E2 axis from its tip towards the origin. So, this way how to rotate the ideas. Now, the rotation about the E3 axis and R3 of theta is the cos theta minus sin theta and then 0 sin theta and cos theta 0 0 0 1 will come. So, these figures illustrate the rotation of R1, R2, R3. So, keep it in mind, you can enlarge to what Rn. So, rotation in n dimension, we have to generalize the rotation from 2D, 3D to n dimensional Euclidean vector space can be intuitively described as fixing n minus 2 dimension and restrict the rotation to a 2 dimensional plane in n dimensional space. As in the 3-dimensional case, we can rotate any plane of the 2-dimensional subspace of R power n. So, this is the meaning of the rotation about the what 1, 2, 3 and so on. Now, we have a definition Given's rotation, let V be a n dimensional Euclidean vector space phi such that V to V and automorphism and transform the matrices. Automorphism in domain to codomain with the same value, and Rij of theta is represented as I suffix I minus 1, 0 and so on. Mean if you say I as a one value and j as a value and corresponding fix it, therefore, this I identity you have to fix. And go ahead with the second row, third row, fourth row and so on, and this can be expressed as n cross n matrix of generalized form, and it will be very helpful to what understand the how to rotate of n dimensional effects, so that you can easily understand the beauty of ML and AI in terms of the rotation. Then here I and j are the bounded between 1 and n, and theta in R, then Rij of theta is called Given's rotation. So, essentially Rij theta is identity matrix In, and Rii is cos theta, Rij is minus sin theta, Rji is sin theta, Rjj is cos theta. So, in 2 dimensional n equal to 2, we obtained a special cases. So, now we have to discuss the properties of rotation. So, rotation exhibit a number of useful properties which can be derived by considering them as orthogonal matrices. Rotation preserves a norm of x minus y equal to r theta x minus r theta y. In other words, rotation leaves the distance between any 2 points unchanged after the transformation. Rotation preserves angles, that is angle between r theta x and r theta y equals the angle between x and y. Rotation in 3 or more dimensions are generally not commutative. Therefore, the order in which the rotation are applied is important. Even if they rotate about the same point, only 2-dimension vectors rotations are commutative, such that r of phi into r of theta equal to r theta into r phi for all theta comma phi belongs to 0 comma 2 pi, 0 included, 2 pi not included. They form an abelian group with multiplication only if they rotate about the same point, that is the origin. So, example is origin only it may obeys. Now, we are based on this rotation and translation and ideas, we are going to apply in modified Gram-Smith process. So, projection is important, and then projection already we explained, projection of x over y equal to inner product x comma y by inner product y comma y into y. So, this projects the vector x orthogonally onto the vector y. So, the Gram-Smith process starting with the vector v1, v2 and so on can be written as z1 equal to v1, therefore, q1 equal to z1 by norm z1. z2 equal to v2 minus projection of v2 over z1, therefore, q2 equal to z2 by norm z2. And z3 equal to v3 minus projection of v3 by over z1 minus projection of v3 over z2, therefore, q3 equal to z3 by norm z3. In general, kth step zk equal to vk minus summation j equal to 1 to k minus 1 projection of vk over zk and qk equal to zk by norm zk. So, here z1, z2 and so on zk is an orthogonal set, and q1, q2, q and so on qk are orthonormal set, right. So, orthonormal, this is orthogonal set. When implemented on a computer, the Gram-Smith process is numerically unstable because the vector zk may not be exactly orthogonal due to round off errors. By the minor modification, the Gram-Smith can be computed them like zk is value vk minus of projection of v2 over z1 and zk minus projection of zk over z2, like that you have to do. In general, Zk minus projection of Zk of Zk minus 1. So, this is the formula for Gram-Smith of modified Gram-Smith orthogonal process in terms of the projection. Now, let us go with one example to understand the process of modified Gram-Smith orthogonal process. So, apply a modified Gram-Smith process to the 3 vectors V1 equal to 1 0 0 1 0 3, V2 equal to 2 2 0 and V3 equal to 3 1 2, and earlier we discussed normal Gram-Smith process and find an orthonormal basis for R cube. So, let us start with the step 1, j equal to 1. We set V1 equal to V1 by norm V1. So, V1 already given 1 0 3 and norm V1 is root 10, and divide them, you have 0.31623 0, 0.94868. So, first step. Second step, j equal to 2 and I equal to 1. So, we have S maps to V2 comma V1 inner product, and V2 you know the given 2 2 0, V1 also already given, dot product them, that is using the inner product, and then we have 2 into 1 is 2 0 and 0, and corresponding we can have what 2 by root of 10, and then we can simplify root 10 by 5, we can write it. So, V2 equal to V2 minus SV1. So, V2 you know 220, and S we generated just now root 10 by 5 or 1 by 5 of 1 comma 0 comma 3, and simplify we can get 9 by 5 2 comma minus 3 by 5, and V2 is maps to V2 by norm V2, and we have the values 0.65293, 0.72548, and third one is minus 0.21764. So, this is the step 2. Now, step 3, you take j equal to 3 and I equal to 1, we obtain S maps to V3 comma V1, then 3 comma 1 comma 2 dot of 103, we have what 9 by root 10, and then V3 is V3 minus SV1, and S maps to V3 comma V2 inner product, so that we have the values, and we have V3 is V3 minus SV1, and we have 12 comma minus 12 minus 4 by 19. After getting V3, take the norm of V3, we have 4 by root 19, which is approximately equal to 1.48748. Therefore, V3 equal to V3 by norm V3, we have the value, and check it out whether they are orthonormal of V1 V2, V2 V3, V3 V1, and it works. Next example, find the basis for column A of conjugate, where A is a matrix, and then 3 minus 1 1 2 minus 1 5. So, the question is posed in R cube, and the columns A form a basis for the 2-dimensional subspaces of R cube. Now, we need only one vector x that is orthogonal to 2 columns in A. Now, using A transpose x equal to 0, the condition is what? You multiply with A transpose. A transpose is 3 1 minus 1 minus 1 2 5 of what? x1 x2 x3 equal to what? 0 0 0, and then you have a matrix like this. So, matrix converted to simultaneous 2 linear equation, 3x1 plus x2 minus x3 of the first one, and second one minus 1 x1 plus 2x2 plus 5x3 equal to 0, and we have to solve this one and manipulate it, and row reduced matrix, you do that, you have the value of 1 0 minus 1 0 1 2, and making use of this we have the values of x1 x2 x3, and we have 1 comma minus 2 1 is the solution, and setting the free variable x3 equal to 1. So, this way we can do that the basis of the matrix. Okay, thank you.